to the bridge. My name is Sam Atman, Principal Agent at Special Circumstances. We're going to talk about the bridge, my suite of software for developing applications for parsing expression grammars. That's about right. Applications for parsing expression grammars. A little programming language that's involved in it. It's a literate programming language. I think those count, especially when you're talking about parsing expression grammars. It's an interesting area of focus, right? What's so nice about parsing expression grammars? Why are you going to write a whole language with them? For them? Well, you know, that would be like writing a whole language around regular expressions. Kind of thing somebody might actually do. Yes, I did bioinformatics Perl a long time ago on Spark stations. So it's a heard of thing. It's been done. JavaScript has been given these regular expressions. Parsing expression grammars. Much more of a profound tool, in my opinion. Not that there is a lack of profundity in regular expressions. Regular expressions, their relationship to deterministic or non-deterministic finite automata and the consequential good behavior of actual regular expressions implemented well is pretty neat. And the concept of regular grammar is very important when you start working with grammars that are not regular. And that is where parsing expression grammars come in. It's one of the places. Part of the package for SafeDocs that Bridge is delivering is a parser construction toolkit. And this is a enriched library for working with pegs called Espalier, which is designed around building parsers incrementally, generalizing further from what we already know about parsing expression grammars so that we can do analysis of grammars that are fed into this system. So middleware with the ability to perform constraints and analysis and rewrite grammars to do interesting and useful things. In significant progress on the incremental parsing toolkit. And we're going to pop towards the end of this thing over. We're going to look at some demonstrations of what's possible with that using a nice test case. Really, I want to show off my grammars. This is, it's an aesthetic thing, I would say, where I started with parsing expression grammars. They look right. And they are. In terms of, well, right, what's right? Yeah. We have come a long way with the parser construction toolkit. I've been applying it in the process of refining it. The white whale, the questing beast here, is to produce useful code from a declarative specification of the structure of a language. Early work on representation led me to the generalized generative grammar format, which has not been the input format that I have favored in my recent work because it allows for unordered and ordered choice. It is a specification and representation format for pathways through language. And the convergence of things like Hammer's very high quality PackRat parser, which does a parsing expression grammar semantic, has led me to focus in the tooling on a string-oriented subset that is based very closely on Brian Ford's original representation of the parsing expression grammar. I believe clarity is important. The first complaint I would have about the wacky Perl style of regular expressions is that it is unclear. And adding an extended format which allows you to put comments into it, that's lipstick on the proverbial pig compared to having a specification that anyone can read and then using that specification to produce code with predictable qualities. The largest difference between a context-free grammar and a parsing expression grammar is philosophical. A parsing expression grammar a context-free grammar constrains the shape of a language. It is stolen by Noam Chomsky from an ancient linguist who worked on one of the first programming languages called Sanskrit. It means what it means, but a parsing expression grammar constrains the shape of an algorithm. It is a set of rules which an implementation must follow such that the data will have a consistent shape. And that turns out to be what you want if you choose the shape carefully. You can look at context-free grammars that way. However, now you're talking about implementations. And context-free grammars notoriously do not a context-free grammar does not specify an implementation, and there is an abundance of implementations of context-free grammars. I happen to think that for the useful subset of languages, and this has been proven for some of the simpler ones like LA, LR1, that a parsing expression grammar may always be constructed for a given context-free grammar, although this has not been done automatically, a deficit I hope to remedy. However, a parsing expression grammar is free to implement as it chooses so long as it fulfills the contract of the specification. And one of the things that makes parsing expression grammars neat is there are two ways to look at this specification. There is the grammar, like the short form terminology, which is the best way to write them down. And there are combinators, which is a credible way to implement the parsing expression grammar and is a great way to think about them. So combinators. They are an implementation technique in a lot of languages, which gives us parsing expression grammars. That has made them more popular than they were before they were invented, if that makes sense. But it, I think, has also inhibited adoption because people think of writing code that then implements a parsing expression grammar as being somewhat inherent to it, whereas the regular expression gets to be its own little programming language that lives inside the other programming language. That was one of the first things that we solved with Expaliar. There you are. That was one of the first things we solved with Expaliar. Expaliar runs on LPEG, which is a implementation of a simple virtual machine that does a backtracking version of the PEG algorithm using bytecode written by the core team behind Lua. And that comes with a vocabulary called the RE module, like regular expression, that is also similar to Brian Ford's original notation. However, the distinction that we started with Espalio is really paying off, is that in the stock Lua specification, well, LPEG is not a part of Lua per se, but it's the most blessed package you can imagine. It may as well be. And so the RE module, which is a standard part of the LPEG distribution, it uses braces to capture things, whereas in Espalio we simply have rules. And if those rules are hidden, they do not show up. And if they are not hidden, they do show up. So capture is assumed. And you end up with, by default, a abstract syntax tree, or if you have decided to capture everything with a rule, which we do in ORB, a concrete syntax tree. So the question I have asked myself is how to generalize beyond this. So we have a specification, it's clean, it's easy to read, and it generates syntax trees. So with a little tinkering with the code itself, I was able to make it also generate, notably, a recognizer, just by, causing some source code to not exist. But then it was time to slow down and work on a combinator framework that goes beyond the combinators that are classic to parsing expression grammars. And I don't have the time, I think, either on the schedule or in my day to get didactic about the existing combinators, so we will assume them. And so we will start with a combinator I call Dji. The Dji combinator is a combinator which takes what I refer to as a meme and a kuf. Everything is labeled in Hebrew. It is. And being a combinator, it returns an example of itself. That's what they do. So it returns a Dji, which, given the familiar kuf that we tend to work with in Bridgeland, will give you an abstract syntax tree, exactly as I was just describing. The meme is where things start to get more interesting. Meme is, right. The Dji combinator, like any combinator, is going to take combinators and return a combinator named after itself. That's what makes them what they are. Dji takes two combinators. They are named Vav and Kuf, and it returns a Dji. In the case that a Kuf is, and for currying purposes, you would lead with the Kuf. You'll see why. So Dji, Kuf, Vav, whereas almost all of the work I have done has been on the Vav side of the equation, which is getting slightly ahead of myself. But given the kuf that we work with in Bridge, Dji will return a parser, and that parser exposed to a valid string in the language, which is constrained by the parsing expression grammar, will return an abstract syntax tree. And kuf, it exists on a layer in the code, but Vav is where all the fun stuff is happening right now. And kuf, it abstracts the action of the grammar, but the middleware layer is in the Vav combinator. And Vav is a combinator of a primitive, which is pe. Pe is the string which specifies the parsing expression grammar, and mem, which is a combinator, and which contains the mitzvahs, the wisdom that is necessary to make good use of a recognized string given a kuf. When we are thinking in terms of mathematics, it is fine to say that every kuf is trivially compatible with every mem. And yeah. In reality, that takes some work, but you got to start somewhere. MAME, the MAME combinator, begins life in our code base as a set of metatables. In Lua, this is how we do anything which you would do with an object in a lesser language. The MAME is itself a combinator and combines two concerns which cut across each other in a way that I think you'll recognize when I explain. So it takes bait and tav. Bait from house, like this is what this word means. This letter is this word, and so the class, if you will, to be Latin about it, is that which is itself recognized when a Dji matches a rule category. And so this is what provides behavior on that basis. And the tav, which you can think of as trait, tav gives us cross-cutting concerns. So for instance, a literal is something which the categories recognized by a particular house, a particular bait, such as string, number, and so on, those which are literal. And this is a opportunity also to provide behavior, but the bulk of the work there is done with flags. It's certainly the case that a particular kind of code transformation can be found to be common to a particular set of properties as defined by tav. That does happen. So this is a principled extension of the existing semantics of the parsing expression grammar world as defined through combinators, which is a great way to define it. It also has advantages in terms of implementation. It has trade-offs as well. And today, ordered choice. As I said, a parsing expression grammar is a specification of an algorithm. It is useful for languages thereby, hence the parsing. However, it is an algorithmic constraint, and ordered choice is the most important one. An operator which might otherwise be called alt, we like to refer to it as choice because, and rather than using a pipe, we will use a // because it is written upon the tablet that Brian Ford carved the parsing expression grammar into in 2010, that every choice will be tried in order. And this upsets people, some people who like context-free grammars. Now, I love context-free grammars, and I am not upset by this. However, there is the special joy of specifying a BNF grammar or what have you, such that if you were to be naive and execute it in the order it is written, you'd get the wrong result, because yes, a grammar is a constraint-satisfying machine, which has very different semantics. So ordered choice is where we start in terms of imposing our own order on the world. The second, which brings us to a second precept and a new location. That is the predicate. Parsing expression grammars use look-ahead predicates, either positive or negative, we call them and or not, in conjunction with the other matching rules. This gives us tail end disambiguation at a low cost, which is something that allows us to express a lot of grammars which would be otherwise difficult given the literal nature of ordered choice versus constraint satisfaction, as well as some less inherent limitations like the lack of left recursion. The third distinct aspect of the parsing expression grammar is limited backtracking. Many matching algorithms will limit look-ahead, which parsing expression grammars do not do. They are capable of bad behavior when it comes to backtracking. The PackRat parser was a response to this. And I said I wasn't going to talk algorithms, but I have some ideas for other approaches. But this is not the limited backtracking which I refer to. Inside of a given rule, a parsing expression grammar will backtrack to try the next rule. However, upon concatenation, it will not backtrack. It will backtrack on choice, but not concatenation. This is predictable. This can be pretty annoying when you realize that you've set a choice that is shorter ahead of a choice that is longer. However, this is the sort of error which one might find with analysis of a parser, which is what I've been working on. So given these properties, grounded in the superstructure of the various combinators which I've described, the Dji Combinator performs a great deal of analysis on simply pay. Although when you look into the implementation, which we're just going to get to, so this is the long-awaited meta parser.